Thanks everybody for being here, and thanks for having us. We're going to present in the next 30 minutes a project that we've been working on, Moritz and I, for the last year and a half. And I was building a firing range for industrial control systems. We did that in our kitchen because of Corona, so there was no way to do it in the office. And that's why that's there as well. We're going to, you can see we didn't bring, so we actually created a model. We didn't bring that, but we're going to show some videos of it later. And then for everybody to take away as well the lessons that we learned. So if you're planning to build something similar in your kitchen, then you know what to do and not to do, hopefully. So roughly that's the agenda for the next 30 minutes. We try to get everybody on the same page, what we understand as firing ranges, what we understand as OT or operational technology. Then Moritz will talk us through how the building of the ICS firing range actually unfolded. We're going to demonstrate it, and then the lessons learned, and then at the end, the questions. About us, I'm Nico. I'm the red team lead for Enviso. I've had my fair share in IT security, and I focus on OT security as well in the past 2 years. And Moritz, if you
Sure. My name is Moritz. I'm part of the software and security team and R&D team at Enviso. And I'm an IoT and ICS enthusiast, and I try and get a hold of as many devices as I can, try and break them.
A few words about Enviso. It's a company that's roughly 9 years old, originally founded in Brussels, now an office in Frankfurt and Munich. We have 150 colleagues at the moment, so it was just a very small subset, obviously. But what's interesting is that Enviso is dedicated to invest 10% of the revenue into R&D, and that is how we can fund this project and the time that went into it. So that's so good that happens. Now, firing ranges. What do we understand as firing range? Of course, it's somewhat a controlled interactive environment. It's an abstraction of a real environment. Think of a toy train, for example, instead of having the real train, of course, to play with. It should be as realistic as possible, and that's what we try to do as well. So you will see that we built a model of a basket bridge, so bridge that has leaves that are lifting. So we tried to model that as closely to the real thing as possible. It should be reusable, so we want to use it for trying out stuff. In our context, that's IT security, so we want to try out attacks, for example, or defense mechanisms. And of course, if we run an attack, we should be able to do it again and again. And it should have that playground factor, so it should be something where we can approach things from different angles and just see what happens if we try it that way, and so on. Why do we need a firing range? So the first that comes to mind, and that was our motivation as well at the beginning, is for training purposes. So we've done a lot of IT security. OT security was fairly new to us back then. So what we wanted to do is to train our people as well and ourselves on how to approach OT networks and how to do security assessments on those. The lab itself, the way it turned out, is very suitable for awareness trainings as well, because it's very visual. So if you run an attack, for example, then you can make some lights stop blinking, or the bridge leaves are not moving anymore, or something else is happening, there's a buzzer going off. So for awareness trainings, for example, very useful for testing if you had any O2 components, for example, PLCs, that you want to try out that you've never played with before. You just plug it into the lab or the firing range, configure it, and then make it work. And then last but not least, for further development of tools, for example, for forensics. So we actually used that lab for forensic training as well, which you'll see then at the end as well, very briefly. Now, OT and ICS, operational technology, are computing systems that are used to manage industrial operations, for example, the manufacturing process, and a subset of that are industrial control systems, so the integration of hardware and software components to control processes for automation or instrumentalization. We do see two candidates here on the slides. On the right-hand side, you see a programmable logic control. It's very difficult for me to say that. PLCs, which is essentially the core unit, if you will, of some automation process. So it's the CPU that runs was connected to sensors and actuators that drives, for example, conveyor belts and so on. And then on the other side, that's an HMI, human-machine interface, where the operators normally oversee the process. They can stop processes or react on errors and so on. So it's just the interaction with the machinery behind it. Now, I bet you're all familiar with IT. What many might not be familiar with is that there's a difference between security requirements for operational technology and IT. Whereas in IT, normally you would probably argue that confidentiality has high priority. So you don't want a customer database, for example, to leak to the internet. That would be very severe. Of course, if you shut down that database, i.e. In regard to availability, then that can have some impact, but it's probably not on that same level. Whereas in OT, it's very different. Confidentiality usually doesn't play a big factor, but availability does. So if you think about power plants, for example, if they just switch off, or steel mill, if that is corrupted somehow, the process, and you need to restart, that might take days. So there's a financial impact, obviously, but also the production behind, just the delay it takes to get everything back up and starting. So availability is key. Now, attacks against ICS, this is the SUNS ICS cyber kill chain. It usually comes in, as far as we know, it comes in 2 stages. The first stage usually goes against the IT network, so the way we know it. There's a resource development phase at the beginning, then delivery, where, for example, phishing emails are sent to somebody working in the office. They click the attachment. The payload installs on the workstation, ensures persistence and establishes C2 communication. And then the adversary can act through the C2 channel and act on their objectives, whatever it may be. Now, if the attack goes against OT, then this is also true. So we are at that stage where we have a foothold on the enterprise. We then recon where is OT located. We identify possible jump servers or DMZs that we need to pass through in order to get there. Once we're there, we locate the targets, we develop capabilities, testing them. So that might be payloads that we want to download on PLCs, for example. Then we download them, install, and execute the attack, which could be the disruption of some manufacturing process, for example. The objectives of those attackers are commonly either the permanent loss of view of control for the operator, so that they can't see the process, they can't interact with it anymore. It could be temporary only for view and control again, but also safety, which is a very important factor, and the same, of course, for manipulation. And the safety aspect is also very different to what we have in IT. There's rarely, at least I don't know of any attacks against IT infrastructure where you would say safety was a concern, safety of people specifically. And we had a case in 2017, which happened in Saudi Arabia against a power plant where they found a malware that targeted safety equipment. It didn't succeed, but the assumption is that if it would have compromised those safety systems, it would have then disabled some of the procedures that would have triggered in case of emergencies. For example, if gas is leaking into the outside, then those safety systems would prevent this. Now, if you modify or manipulate that, then you couldn't or you wouldn't prevent it. So this would not only be then, of course, an issue for the provider here, but also for everybody that lives around the power plant if hazardous gases are leaked to the outside. Now, Moritz is going to talk us through our ICS firing range, please.
Right. Thanks. So how did we actually go about building this ICS firing range? Well, let me maybe first start with what we had in mind, what were our driving motivation behind building this. So as Nico pointed out, we have a difference in security requirements in OT comparing to IT, right? And we then have to adapt those differences obviously into our approaches to performing security assessments, right? So most importantly, what we have to pay attention to is, of course, the safety aspect. We can never know really what is the safety impact of hacking a OT device if we don't have accurate depictions of the documentation of what actually those devices do. So what we want to do and what we then succeeded to do is to build a playground where we can perform internal training and to then perform research and development on this. So we developed the concept of a water treatment plant, which was comprised of 3 water filtration units, and then as actuators, pumping stations, which pumped water from one filtration unit to the next one. And to back this up and to represent a more or less realistic environment that drives this, we had also SCADA and an enterprise network behind this, fully virtualized. So when we worked on this, we were then contacted by a client who said, well, we really like what you're doing. We would like to have this for us as well, because we are actually operating critical infrastructure, and as part of this, they operated bridges, passkey bridges. And they wanted to have such a playground for their own digital forensics and incident response teams to find out, okay, what happened post-compromise? and this should be also a mobile solution so they can then do those trainings at different sites. So we adapted our concept to do BASCO bridges, and this was our very first concept. So here you can see it's basically an aluminum frame on wheels. In the very top there you have a scale model of BASCO bridges. Then in the lower half there's a front and a back side. In the front side you see OT equipment such as PLCs, power distribution, power supplies. And the back there, the area that you can't really look into because there are black panels, there should be the virtualization server. So we were familiar with building virtual environments. We were somewhat familiar with assembling stuff, but not very much with 3D printing and just designing this bridge, for example. So that's what we started with. Here you can see in the center there's our CAD model of the bridge. You saw there were two bridges, right? So the other side is just a flipped version. And we 3D printed those. So what I would like to point out here in particular are the most prominent parts. So here you can see the bridge leaves, which lower and raise. There are switches that are our sensors, which detect whether our bridge is now in a fully opened or fully closed state. And of course, we also have traffic lights and a road barrier that goes up and down. And when all of this works, it's synced so that there's a process where the bridge opens and then the traffic barriers are down and the lights indicate that no traffic should happen here. And that should all hold and then they go back down again. The road barriers go up again and then traffic should commence there. As we said, as part of our title, we built this in our kitchen. This is my kitchen and that's my oven actually. Much to the dismay of my wife, we did this in my kitchen just to keep those prototyping intervals very, very short. So typically I would design a model in the evening, kick off the print. This would take hours and hours and hours. And sometime in the afternoon it would be done on the next day and I could take it out of the printer and try and assemble it and see if it works or if I have to adapt anything about it. So at that point we got a model, but it couldn't really do anything on its own. So we needed to do more to it. We first assembled it. Then we got a hold of those aluminum profile beams and built the frame and the backplate for the electric cabinet inside. We put all the OT equipment in there, wired everything together, installed the bridges and wired them. Those are roughly 50 individual connections that we then put down to the OT equipment. We put panels to it because they look nice and they, of course, hinder you from actually reaching into it while it's operating. You shouldn't do that. Some sweet backlighting we put in there so you could actually see something because it was getting dark. And we did a lot of testing, an awful lot of testing. Many hours were put into debugging all of this. And we at some point even had to resort to using an oscilloscope, as you can see here, to debug the motor control signals because they were not really in sync and they were off. So we had the physical build, but this only gets you so far. What we were really interested in was actually powering it with a fully virtual environment in the back, right? So let's get to the network infrastructure that was then used, for example, for kill chains. This should again be somewhat realistic and it should be extensible. So here's our network infrastructure. Those are 4 networks. The networks in the dotted rectangle, they're mostly virtual, while the OT network down there is mostly physical. Let's go through all of those. They were implemented in an ESXi server, and they all use OPN sensors for segmentation and segregation, so just for routing and for the firewalls. Now let's see. So in the enterprise, we had an enterprise network, we had a domain controller and a domain joined office workstation, which we heavily abused for initial foothold in our kill chains. So there would be, for example, the case where we had a phishing mail, and the attachment of this phishing mail got opened, and then it was compromised. There was also a web UI that would allow office workers to then have a look at what the process is currently like at the bridge. Then in the SCADA network, we had an operator workstation, which would allow you to more closely monitor what's actually going on in the process taking place, like what are the individual pieces of the bridge doing. There was an historian which actually grabbed production data and stored it in a time series database and a jump host, to which we will get back later. The DMZ honestly stayed very empty for most of the time and still is. We plan to put a Windows update server maybe there, but we didn't. And then in the OT network, we have, of course, all our OT equipment. So there are 4 PLCs, one rather new model. So there was an S7 1500. They were all Siemens PLCs. That was the area supervision. That one would orchestrate the other ones. Then there are two more or less budget models, S7 1200s. They were the lifting substations, and they drove the leaves and the barriers. And then lastly, we got a legacy model, the S7 300, which is, if I recall correctly, close to 30 years old. And that drives actually the lights. And of course, we have the manual override HMI, so where you can actually tap and change stuff around physically. We also built in a CCTV system using Raspberry Pis and pan tilt cameras. And here's one last virtualized station, so that's the engineering workstation. That will be used to actually program the controllers. And that would also be more or less the last step in our kill chain, which we could compromise to then effectively compromise the PLCs, because this one could program those, right? So, knowing about this, let me show you what it really looks like when we all assembled it. Let's see if the video works. Nice, okay. So, here you see the model on top, and it will just start its cycle of lowering the barriers. And here we can see in the HMI that what you see on screen is actually synced to what's going on in the bridge model. So now, for example, they are raising again. Taking a look inside, we can see a whole bunch of wiring, stepper motors, and actually also active cooling. We had to do this a whole bunch over the whole firing range because it got really, really hot. Then there in the back, you can see a desktop case. So that's our ESXi server. There's the big switch and an AP for wireless and easier debugging. And that's pretty much it. And that's what it does all the time. And now at that point, we can go there and try and compromise it. Then we have some backup slides in case the video wouldn't work. You can skip those. Now, for the lessons learned. What did we learn? We learned a whole bunch. First of all, regarding the ICS lab setup, we learned that especially with the hardware compatibilities and dependencies that you got, assembling such a firing range can get somewhat complicated when you're not a domain expert. We are not ICS engineers. We are not mechanical engineers. So those were things that were rather new to us. You have to take several things into account, right? So power supply, what kind of power source do you need? What kind of protocols do those devices support? What kind of protocols are relevant to your cases, to your scenarios maybe? So this can be quite a bit. Then the software licenses are quite pricey. We'll get into this later. And a practical thing that we figured out was that the stepper motors, they tended to overheat, and that was actually very bad. For 3D printing, again, we didn't really do this prior to this project, so this was all new to us. We are not mechanical engineers, so especially the part with the bridge leaves opening and closing, this was quite challenging for us to develop, to design, and then to implement, and to make sure that it doesn't break, because it broke a whole lot. And then factor in the fact that printing is very time-consuming. As I said, I would kick off a print at night, and it would maybe be done the afternoon next day. We had prints, we had individual parts that took up to 3 days to print, so 72 hours. And if anything goes wrong, you're done. It's bad. And also, if you're not an expert in 3D printing, you will run into a whole lot of problems, ranging from A to Z. So we had, for example, problems with the prints not sticking to the print bed. So the print would just go, and the filament would go all over the place, but it wouldn't be there where you actually needed it. And then to have models that you can actually adapt to your needs and to modify further, you would do this in CAD. Again, we didn't know CAD prior to this, so this was also quite a whole bunch to learn. But also, there were practical challenges. So this is the firing range. It was 80 centimeters by 120 centimeters in size. Only the frame was a meter in height. And if you factor in the wheels and the models, it's more like 1.5 meters. So every time we wanted to move it anywhere, we needed to get a very, very big van, which was mostly empty, but we needed it to put it there upright. So we needed the vertical space. And then also we had problems with the models, right? So here you would see that the road barrier would collide with the lights up there. Wasn't very nice. The stepper motors were heating up. There was the wiring, which was all over the place. And there was very little clearance for the moving parts. This was iteration 1. So we iterated one more time. And there, iteration 2, we addressed all of those problems. Here you can see those lights are set back, so they don't collide anymore. There are actually fans that we built into it, so there's active cooling. And you can just let it run for hours now. It won't overheat, which is nice. If you want to do maintenance, or if you have to do it, there's a central backplane where all the wiring is just going, which is nice. And of course, the clearance. We have way more clearance here, and there are no more parts scraping on other parts. So that's great. What's the bottom line, though? We started this in January 2021. We put more than 1,000 hours of manual work into it. More than 900 hours additional to the first 1,000 hours, which is net 3D printing time, and a whole lot of this time was overnight. And over the course of the whole project, we burned through more than 8 kilograms of filament. We spent roughly $18,000 US on the whole project. Most of this for hardware, but as you can see, $3,500 US dollars just for licenses, which I hadn't expected in the beginning, but here we go. And we actually destroyed some stuff over the course of the project. So there were 2 stepper motors that we actually burned through, one PLC that died, presumably from faulty wiring, and one motor driver that also died due to faulty wiring. And at times we lost parts of our sanity, to be honest. And at that point, I would like to hand over to Nico again about what's next.
What is next? Thanks, Moritz. Okay. So if you paid attention, I'm sure everybody did, the video that we showed differed from the 3D model, for example. So if it wasn't clear, we actually created 2 iterations. The first one, where the problems arose that Moritz mentioned, and then to make it better, we created a second model. So there's actually 2 models. What we should be doing is creating a third iteration to address some of those points that are still not that great. So, for example, mobility is an issue. You need still to rent a van to transport it, and it was supposed to be very mobile. It really isn't at this moment. So it could be, for example, that the disassembling of the entire firing range is somewhat easier. That parts could be taken out of it. Also, the modularization is something that we had in mind. For example, so we're talking about bascule bridges now, but maybe we want to have a small town or toy train or something running on top without changing the hardware underneath, because it's most likely going to be very similar. So we just would replace the top on the model, i.e. the bridges, with something else, and then download new software on the PLCs, and then it should be done. So this is something that could be done in a third iteration. Whether or not we're doing this, we have to see. It's not clear at this moment. What we certainly will be doing is develop more scenarios. So the intention of this firing range was to use it for training, and we've used it for forensics training in OT, for example. So we had a two-day workshop on this, which were quite great. But we currently don't have scenarios, for example, for penetration testing or red teaming in OT. So this is something we want to work on as well. Similarly, monitoring and detection in OT, I think, is a topic that's very interesting, and many people are interested into looking at that as well, even in our company. So for this, developing a scenario would be very worthwhile. Now, if you're interested in OT or want to know more about this project, we're here to answer questions. Of course, we're going to be outside after this talk. You can reach us via these email addresses. If you want to know what Enviso does for ICS, there's a page for that as well. And otherwise, we have 2 Twitter handles and a blog that you can look up. On the blog, there is a series about this firing range as well. So parts of what we presented, a bit more detail as well in some areas. Just check it out and see for yourself. Good. Any questions?
Thank you. So, do we have questions? I'm sure for the audience. The front microphone, if you want to take any questions. So, okay, I see Jen. Please come up.
It's hella cool. So thank you very much for this. I was wondering, what other materials did you consider when putting this model together? Like, did you think about Legos or something like this, or did you go directly to printing?
I think Lego was in talks. There was talks about using a bit more wood as well to get some parts done. I'm not sure why we did not decide on Lego in the end, to be honest.
Not sure.
I think it just looks cooler if it's 3D printed.
Maybe it was occupied by children or something.
Yeah, as well. Yeah. I think probably the possibilities it's just a lot more possibilities to create stuff if we have it 3D printed and we're fully in control of how it should look like, and especially the smaller parts than they're needed.
And I'm a long time no Lego player, but I remember there were no real bridges, moving bridges. So you only had trains and stuff.
Okay.
Do you have any similar projects, like other companies doing similar test ranges, firing ranges that you exchanged ideas with?
And honestly, we didn't. We know that not for bridges, but of course Siemens, for example, they have developed also test environments for traffic controls, for example. But it's a different price range as well, and I'm not sure if they would disclose too much about their projects towards us. But no, actually, I don't know.
Maybe you find somebody from Siemens over a coffee.
Yeah.
So do we have any other questions? Okay, one coming up.
Most of the ICS or the OT environment will have some physical control over the process, not only that some malware can shut down the process. While building your fire range, did you also consider physical controls, like you detect some attack or something, and then there is somebody who is putting out switch, or like why Triton did not succeed, and also scenarios like that?
So there's the HMI, if you meant that. So there's the HMI for direct control.
So, for example, if you consider the Triton thing, it tried to shut down the safety system, but of course it did not succeed. There were also physical controls on site and all to avoid these. Were you considering this to build in the firing range? Because that would be more realistic in an OT or ICS environment, right?
Yeah. We can't put everything in that model. That's, I think, probably that's difficult. So we restrict ourselves to the couple of PLCs that we have in the HMI, and build the scenarios around that. So additional hardware equipment, we did not plan for, at least in these situations so far.
Yeah, this is why, because it would not be practical to imagine that, only through an enterprise network you get into the OT network, because there would always be some physical control over the processes as well.
Sure. So you're saying that the attacker, they skip the IT part and they go straight to OT and carry out the attack from there. Is that what do you mean?
No, I meant there would be some physical control that cannot be reached by attackers to avoid such scenarios, and maybe in these kind of projects we can also consider this.
It could be implemented in this. Sure. Yeah. I mean, it's also extendable. If this is a project for the future, I think it's a good idea to include.
Thank you.
Thanks.
And are you going to put this on the internet for us to test as well?
It's not.
I mean, you need. I guess you need data for forensic analysis. So you just put it on the internet and wait for us to test it. Maybe
we'll think about it. Yeah. Okay.
Okay. Then thank you very much.
Thank you.